Welcome to the False Discovery Rate and Overview. My name is Phil Anderson. I'm a professional data scientist and part-time grad student at Texas A&M University. This talk is something that I put together as a part of my master's degree at Texas A&M. That's part of why you're going to see a lot of A&M branding on the bottom of the slides. But it's going to be about the idea of multiple hypothesis testing in statistics, and then specifically about something called the false discovery rate. One of the things that I learned as I was researching this topic is that there's a bit of a lack of generally accessible information about it. And so I put this together and I'm sharing it on the internet, largely because I wish that I had had access to something like this when I started learning about it. As far as what I'm going to cover in this video, it's right here. So the first thing I'm going to do is start off with a little bit of context about what the multiple comparison problem is. I'm then going to talk about what the false discovery rate is, with a special emphasis on a procedure introduced by two statisticians named Benjamini and Hochberg. I'm going to talk a little bit about critiques of their procedure, and then some proposed enhancements that different statisticians came up with. Okay, so as far as context goes, the first thing that we're going to do is look at what the problem of multiple comparisons is. So we're going to start by looking at this familiar hypothesis testing framework. And so I'm kind of assuming that you've seen this in some capacity before. But one important thing to note here is the notation, because this is the notation that I'm going to be using throughout the rest of this presentation. The important quantities here I'm kind of circling with my mouse. V is the number of type 1 errors that you're encountering. And the term type 1 error is equivalent to false positive and false discovery. So I'll probably be using those interchangeably. Those all mean the same thing. The other important variable here is R. R is the number of hypotheses that you are going to reject. M sub 0 or M naught is the number of true null hypotheses. That's not something that the practitioner is actually going to know. But they will know M, which is the total number of hypotheses that are being evaluated. So going through a few fundamental concepts to hypothesis testing, I want to start with the p-value. And so the p-value is the probability under the null hypothesis of obtaining a test statistic at least as extreme as the value that you observed. This has an inherent relationship with type 1 error, and its intended use implies single inference. And so what I mean by that is when Neyman and Pearson and Fisher were coming up with this hypothesis testing framework, some of the situations that we encounter today were not necessarily on their radar. And so if you think about what conducting a hypothesis test used to involve, it was very manual, it was all hand computation. And so when the idea of a p-value was introduced, it was really associated with the idea that you would be conducting one test at a time, not necessarily several. That situation, though, of conducting several tests simultaneously started to arise probably in the middle of the 20th century, although it had come up a little bit before that. A really prominent example of this is post hoc comparisons in ANOVA or ANCOVA. So if you're examining a factor along some continuous response and your factor has 3 levels in it, you're going to have to do some sort of post hoc evaluation after the initial f-test to determine whether or not those levels are different from each other. This multiple testing scenario does introduce an inflated risk of type 1 error, and that's typically known as the family-wise or experimental error rate. That's commonly abbreviated as FWER, and will be for the rest of this presentation. This is more formally defined as the probability of making at least one type 1 error amongst M independent comparisons. And so you can actually see our notation from the previous slide showing up. We're seeing the probability that V is greater than or equal to 1. So the probability that having a type 1 error is greater than or equal to 1. And the expression for that is given at the very bottom of this slide. And what we have is alpha, or the test size or significance level, and alpha sub e is referring to the family-wise test size. That's given as a function of two things, m, which is the number of comparisons that we're making, and then alpha sub c, which is the comparison specific test size. And so to get a better handle on that, I have some visualizations. And so on the x-axis is the number of comparisons that are being made, and then on the y-axis is the probability of achieving at least one type 1 error. And so we can see at the end of this slide, or the end of this graphic, once we have 20 comparisons, our probability of having a type 1 error is over 60%, which is fairly large. When we start getting into hundreds of comparisons, what we can see is that family-wise error is a near certainty. And so once we get to around 100 comparisons, we've asymptotically approached a value of 1. And the more interesting question here is not actually whether or not we're going to get a type 1 error, but rather how many type 1 errors we should expect. So this problem was not unnoticed by statisticians. They started working on it in the middle of the 20th century. And there are two general classes of procedure for handling this. The first one is a single-step procedure, and the most famous example of this is something called the Bonferroni correction. And so the Bonferroni correction is very straightforward and very popular. One drawback of it is that it's overly conservative. And so that's given by this expression. And so what we're going to do is set the individual comparison level test size to the desired family-wise error and divide that by the number of comparisons. So if you're making 2 comparisons, for example, and your family-wise error rate is 0.05, you're going to divide that value by 2 to arrive at 0.025. But you can see how when m starts to get large, that starts to become very strict. The second class of procedures is called sequential. These are known as step-up or step-down procedures. And these tend to be a little bit more powerful. And one example is the Holm-Bonferroni method. I'm not going to go into too much detail because we're going to see an example of a sequential procedure later. That's why I've actually bolded the word sequential. But these are procedural approaches that are going to order the p-values and basically evaluate a given array of p-values at each index of that array compared to some quantity. And that's a lot it's a lot without an example, so we'll see one later. But just know that these tend to be more powerful than the single-step procedures. And there's a whole host of these things. There's dozens of them that are all situationally appropriate. And so these are some examples here. Chaffee, Sue's Best, Tukey's HSD. Again, in particular situations, each of these can be more or less powerful than the others, or appropriate. So one caveat of these family-wise error rate controlling procedures is that they were designed for a handful of multiple comparisons. So when we say handful, we're usually thinking at most around a half dozen. Of course, in the world today, we can imagine situations where we might be conducting many more than a half dozen hypothesis tests. And so the one example where this comes up a lot is genomics. And so I'm not a genomics practitioner or professional, but the general idea is that you can compare multiple samples of genetic material, and you want to compare those across different submodules. And when you do that, you can use something as simple as a t-test. But the thing is, there's hundreds or thousands of submodules that you might want to compare. And so you can imagine that starts to add up very, very quickly. So the question that statisticians are now faced with today is that what do we do if we find ourselves with hundreds or thousands of hypothesis tests? And the answer that has been arrived on is to control something called the false discovery rate. So what is the false discovery rate? Well, if we look back to our hypothesis testing framework, we're going to define the FDR as the proportion of rejected hypotheses that are erroneous. And so actually looking at this table, we're going to say that this is equal to V, the number of type 1 errors, over R, which is the number of hypotheses that we have rejected. So the most famous way of dealing with this and sort of controlling that quantity was introduced by 2 statisticians named Benjamini and Hochberg. And so their full names are given here, but they introduced this famous method in a paper called Controlling the False Discovery Rate, a Practical and Powerful Approach to Multiple Testing. And to say that this paper is a big deal is an understatement. It's actually, by citations, one of the top 10 statistics publications of all time. It has just under 50,000 at the time of this video. And the paper takes the view that we should attempt to control the expected proportion of errors amongst all rejected hypotheses. And it'll become clear in a second why I've bolded the word expected. This results in weak control of the family-wise error rate that we looked at, but it's actually more powerful than procedures that strongly control the family-wise error rate, which is pretty nice. A more technical definition is given here. So looking back at our hypothesis testing framework, we're going to introduce a new unobserved random variable, Q, that's simply defined as V over R. So again, the number of type 1 errors or false discoveries divided by the total number of rejected hypotheses. Benjamini and Hochberg are going to focus on the expectation of Q. And so this variable Q sub E is defined as the expected value of V over R. And an alternative formulation for that is the expected value of V over R, conditioning on R being greater than 0 times the probability that R is greater than 0. And the reason that I'm calling that out is going to be clear in the next section. But the expected value of V over R and this expression down here are equivalent, although one is quite a bit longer. So the procedure that Benjamini and Hochberg came up with is actually pretty short and it's pretty straightforward, but it's still very powerful. So the first thing we're going to do is if we're given an array or vector of m unadjusted p-values generated from m different hypothesis tests, the first thing that we're going to do is order those in ascending fashion. And so this is known as linear step up. The next thing we're going to do is iterate over that array, and for each element in it, we're going to calculate this quantity on the right. And so that's the index of the array starting at 1, divided by the number of elements in that array, or its magnitude, or the number of hypothesis tests that we're conducting, times Q star. And Q star is the expected proportion of false discoveries that we would like to have. And so this convention is usually set at 0.05, but you could set it at 0.1, 0.01. It's similar to a p-value in that respect. So once we've calculated this quantity, we're going to compare the p-value at every element in the array to its quantity that we've calculated. And we're going to reject the null hypothesis when the p-value is less than the calculated quantity. And so I think that's a bit much to see without an example. So we're going to jump to one here. And so this is a example that I put together in Python. And so this procedure exists as a preset function within scikit-learn in Python, but it also exists in pretty much any statistical software you can think of. R, SAS, Stata, those all have implementations. So the first thing we're going to do is import our data. And so this is actually taken from an example within the Benjamini-Hochberg paper, but they have a data vector with a length of 15. And so these are p-values from 15 different hypothesis tests. And so these are printed out here. So the first thing we're going to do is order the array that we have in an ascending fashion. And so we can see that we're moving from 0.0001 all the way up to 1.0. The next thing we're going to do is create a loop generating that quantity that we looked at before. And so that's actually given echoed down here. And so index 1 is the first element divided by the total number of hypothesis tests, or 15, and then times that Q star value of 0.05. And so we can see that when we multiply all these things out, we get 0.003 repeating. When we move to the second element, we're getting 2 times that, or 0.0066 repeating. We're then going to bring everything together into this table here. And so we have, first of all, our index starting at 1. Python does not start at 1, which is why it has that 0 there. The p-values that we were given, and then what I'm calling an adjusted p, which is that quantity that we made. And then a rejection indicator. And so what we're doing is we're rejecting the null hypothesis when this p-value is less than the adjusted p-value. And so we can see in this example that we're rejecting 4 different hypotheses. Now, interestingly, if we were to use one of the previous methods that we talked about, specifically the single-step Bonferroni correction, we would divide all the p-values by 15. And if we did that, we would only reject the first 3 hypotheses and not the 4th one. This is significant because the p-values that we're going to care about a lot tend to be on the margin. So for example, any procedure will probably say that this p-value of 0.001 is significant. Like, that's not really in question, but there is a question between whether or not this guy should be rejected. And so if the Benjamini-Hochberg procedure can identify successfully these sort of marginal situations, it's going to be a really valuable procedure for us. So when Benjamini and Hochberg produced their 1995 paper, they also conducted a power test to evaluate how the procedure that they had come up with compared with other leading family-wise error rate correction procedures at the time. And so the two that they used were that Bonferroni correction that we had looked at, and then another procedure introduced by one of the authors, Hochberg, in 1988. And so they looked at power testing across a variety of scenarios. And by power, I just mean statistical power or the ability of a test to detect a deviation if there in fact is a deviation. And so what they found was that the statistical power of the Benjamini-Hochberg procedure was uniformly larger, so larger across the board, than the two leading family-wise error rate methods. They also found that the advantage increased with the number of tests that you were evaluating. And so this is given right here. And so the reason there's different panels in this test is because they looked at different proportions of true null hypotheses. But what we're looking at is on the x-axis, the number of tested hypotheses that somebody might evaluate, increasing as we go to the right. And then on the left, we have the average power. And so what we're seeing is the solid line is the Benjamini-Hochberg procedure, and we can see that in every single one of these panels, the power is higher. We can also see that as we increase the value of the x-axis, or as we increase the number of tested hypotheses, there's a larger deviation between the Benjamini-Hochberg procedure and the two competitors, which is what they found. So like most things in statistics, this procedure is not without its critics, and it's not without potential enhancements. And so the main critiques of this method are given here. The first thing is that the procedure depends upon the independence of hypothesis tests, which is often an unrealistic assumption. So if we're conducting 1,000 hypothesis tests on different components of the same genetic material, it's probable that there is some relationship amongst those different pieces of material. The second thing is that the BH procedure controls an error rate expectation rather than an error rate probability. This isn't necessarily a critique as much as it is just a point about the procedure, but one alternative method that we're going to see in a few minutes is going to be Bayesian. And so Bayesian procedures tend to focus more on probabilistic outcomes, and so the author is just pointing that out. In addition to that, the selection of Q, much like the selection of P, is something that's subject to debate. So there could be a question of, should we use 0.05? Should we use 0.1? That's something that reasonable people could argue about for 15 minutes. Another critique is that the BH procedure over-controls the false discovery rate and does not in general minimize the false negative rate. So depending upon the application, this may or may not be important to you. And then finally, the power can be improved in non-sparse cases by adaptive procedures. And we're actually going to see an example of an adaptive procedure right now. So this was introduced by one of the authors, Benjamini, along with two other individuals, Krieger and Yekutieli, and they introduced this adaptive FDR control method. And so their premise is that if we had an estimate of M naught, or the number of true null hypotheses, we could improve the power of the Benjamini-Hochberg procedure. So what they're going to do, or what they're saying, is that an adaptive procedure in this setting is first going to estimate the number of null hypotheses, M naught, and then use that estimate to revise an existing multiple test procedure. And so the method itself is given as follows. Step one is we're going to use the original BH procedure or method to find K, or the number of rejected hypotheses. And so in the example that we looked at, K was 4. Step 2 is to estimate M naught hat, which is given by M minus K. And so again, thinking back to that example we looked at in GitHub, the total number of hypotheses that we evaluated was 15, and the number of rejections was 4. So M naught hat is equal to 11. Step 3 is to again use that original procedure that we looked at, but now we're going to take Q star to equal Q prime times M divided by M naught hat. And Q prime is given as 0.05 in our case. So when we go through this, we have the following outcome, and that's the BKY method is more powerful than the BH method when a considerable proportion of the hypotheses under consideration are false. It's less powerful, however, when there are very few false hypotheses. So this is something that as a practitioner, you would need to have some sort of idea about before you went into using a particular procedure. The next method that we're going to look at is something called the positive FDR, which was introduced by someone named John Story in the early 2000s. So Story takes the view that the BH procedure is fixing alpha and then estimating k hat, or the rejection region. He actually does the opposite, and he's going to fix the rejection region and then estimate alpha. So in other words, he's trying to control the probability that the null hypothesis is true, given that the test rejected the null. And the notation for this is given below. And so you'll remember when we were looking at the FDR technical definition, we saw this expression up here. The PFDR is actually given by a component of that, but we've taken away the probability that R is greater than 0. And so this term positive in positive false discovery rate is taken from this positive conditioning here. Story also introduced the PFDR analog of the p-value, which he called the q-value. And so the q-value is the expected proportion of false positives amongst all features as or more extreme than the observed one. And so to give an example of that, a q-value of 5% indicates that 5% of the significant results will result in false positives. And so I have an example here. This was put together with an R package called q-value. It's quite nice. And so this is our original vector of p-values here. So you might remember this 0.001. On the right, we have the associated q-values for all these things. And the interpretation is such that any record above and not including record 6 has a 5% chance of being a false positive. I'm not really sure what 5% of 5 records means, but you can think that if you had a larger example of maybe 100 hypothesis tests, then that becomes a little bit more clear. And so one advantage of this procedure, while it is, I haven't talked about this, but pretty computationally intensive, it's generally more powerful than the original method, which is definitely an advantage. So the next thing here is something called the local false discovery rate. And the local false discovery rate for a particular test is the empirical Bayesian posterior probability that the null hypothesis is true, conditional on the observed p-value. And so I'm going to kind of skim over this because talking about empirical Bayes opens up a whole can of worms. But the expression is given here, and it basically boils down to this guy on the right, and that's the probability that we have a null hypothesis times a ratio of null and non-null densities. And I think the coolest thing, or the easiest way to see this, is just to see the output. This is something that also can be calculated with the q-value package. And because it's Bayesian, it has a very nice intuitive probabilistic output. And so you can see record 4. What this is indicating in this LFDR column is that this record has an 11.2% chance of being a false positive. So I think that's pretty nice. The last method that we're going to talk about is the Genovese-Wasserman exceedance or false discovery control method. And this is probably the least well-renowned of the ones that I've looked at, but I think it's pretty cool because it has a very clear situation in which it's useful. So we've seen that the false discovery rate is a sort of expected value of something that Genovese and Wasserman are calling the false discovery proportion, or FDP. And so again, that's just type 1 errors divided by the total number of tests we're looking at. Their exceedance control is attempting to bound the probability that the false discovery proportion is greater than a particular threshold rather than an expectation. And so the reason that they're doing that is because there's variability in sampling of the false discovery proportion about its mean. Controlling the false discovery rate, such as Benjamini and Hochberg do, permits large deviations in the false discovery proportion with a very high probability. Through this exceedance control, we're basically bounding the probability of these large deviations, which is resulting in a decrease in power, but then stronger constraint on tail behavior. So if you're thinking about, as a researcher, if you're concerned about some sort of tail event throwing things off for you, you can use this method, and you're basically accepting a decrease in power, but if that's the big concern as a sort of extreme event, you're sort of reining that in. So to summarize all these different methods, I've put together this table. And so the top one is the original Benjamini-Hochberg method. One pro of this is that it's very popular and straightforward. One con is that more recent procedures introduced within the last 20 years can be more powerful. The next thing that we looked at is the Benjamini-Krieger-Yekutieli adaptive procedure. And so one advantage here is that it's more powerful than the original when many hypotheses are false, but it's less powerful when few hypotheses are false. And so if you as a practitioner have an idea of that going in, you can choose to use that. The positive false discovery rate is something that is more powerful than the original procedure, but is very computationally intensive and has fewer software implementations. The only example of this that I was able to find with an admittedly cursory search was R, which is certainly good for all your statistical needs. But if you want to use something such as Python, that might not be there. The local false discovery rate, one pro of this, is an intuitive probabilistic interpretation that statistically minded individuals might find favorable. One downside of this is that stakeholders, whoever you're working with, may not hold Bayesian literacy and may not be accustomed to thinking of things with a probabilistic viewpoint. So that can be a barrier to implementation, which you want to avoid. And then exceedance control is one pro of that is that we do get a constraint on tail behavior, but we get something that's less powerful than the Benjamini-Hochberg method. And so that's the primary material. There is an appendix, and I'll link to this PowerPoint in the notes. But a few things you might want to look at are references. A lot of these are really good if you want additional material on the false discovery rate and anything that I've talked about. I also have another example, and I'll link to the GitHub as well. It's a more full example of the Benjamini-Hochberg method. And then I also list some notable software implementations that exist with this. And so the most popular place you're going to find this is R, which is unsurprising. You can click this top link to get a full list of those. And then I talk about the link to the Q-values package specifically, because I do like that one quite a bit. If you're using SAS, proc mult test talks about this a lot. The documentation for this is actually quite helpful. So even if you're not going to use SAS, the documentation for all of its procedures are really useful. And then Python has stats models and scikit-learn. And then, of course, you can use the code that I wrote as well if you want. And then Stata has an implementation as well if you're using that. So thank you for watching. I hope you learned something, and have a good day.